Okay, so let's look at vapor compression refrigeration systems now. Essentially, these are reversed Rankine cycles. So if I just think component by component of the Rankine cycle and reverse it, so a turbine, if I reverse that, is going to be a compressor. Whereas a turbine produces power and decreases the pressure of the gas, a compressor is going to take that same gas, but it's going to increase the pressure and require work input. A boiler, okay, another key component to a Rankine cycle, a boiler took a liquid and turned it into a gas, okay, added heat. This time I'm going to take a gas and turn it into a liquid, removing heat. Now, my condenser, my reverse of that is going to be an evaporator. This is very similar to a boiler. It's going to change the state from liquid to a vapor, but the difference is a boiler requires fuel input, whereas an evaporator is going to do it just using ambient conditions for whatever the evaporator's ambient is. Maybe it's the inside of your refrigerator. Now, the pump. This is where it gets to be a bit of a difficulty. Because if I reverse a pump, which required power input and is going to take a liquid from a low pressure to a high pressure, I would want something that would take a liquid from a high pressure to a low pressure and produce power, which would be a liquid turbine. But a liquid turbine is a very expensive piece of equipment for what you're going to get out of it. It's going to cost way more than it's worth for this sort of an application. And it's going to also always be a maintenance issue. So instead, we just simply put in an expansion valve. An expansion valve will take this same liquid and put it through what I call a torture chamber to simply drop the pressure. Okay? So this is going to be one major difference between simply running our Rankine cycle backwards, okay, and this is a cost-saving measure, the reason we do that. Now, if I do all these things, this is sort of what it would look like. So I'm going to bring my stuff into my backwards turbine, which is a compressor. I'm going to now go through my backwards boiler, which is a condenser. It's going to have heat output instead of input. I now need to drop the pressure because it's a liquid. I'm going to run it through this expansion valve, and then I'm going to bring it back to my original state. So I need it to go back to being a gas. I'm going to run it through an evaporator, which is like a boiler, but the heat input is coming from something other than a fire. Okay? So if we try analyzing this, then what I'm going to have is that I have states 1 to 2 are reversible and adiabatic compression. This is my compressor, and my ideal is going to be adiabatic plus reversible, and so that means it's isentropic. Also, I'm going to have just one stream in, one stream out, work being required, so the work of the compressor will be H in minus H out. If I want to turn that into power, I'd multiply by the mass flow rate. Now, my condenser, this is isobaric, constant pressure, heat transfer out. It's going to add heat to the warm reservoir. So if it's my refrigerator, it's the outside of the room. If it's my air conditioner at my house, it's the outside of my house. So if it's constant pressure, which is the assumption we've been making for most of our heat transfer devices, it's just really flow through pipes, and the pressure drop will exist. It's not non-zero, but it's very small. And so assuming constant pressure works for calculation purposes of the thermodynamics. So the Q is going to be my Q at the high temperature. It's going to be out of the system, but it's just a single stream flowing, so H3 minus H2, using the nomenclature here in this picture. The isenthalpic pressure drop, H3 minus H4, is what's happening across the expansion valve. If you'll recall, on an expansion valve, we'd look at that and say, well, there's no real change in kinetic energy or potential energy. There's no real heat transfer because it's small. Plus, I probably will insulate it anyway. And the work is 0. There's no moving parts. And so what I'm left with in the first law is that the enthalpy in is equal to the enthalpy out. And so I'm going to use this to calculate across the expansion valve. The pressure will decrease. Now, the bad news is these are always irreversible. You cannot build a reversible expansion valve. If I go through the expansion valve the other direction, I still get a pressure drop. Okay, I'm not going to go back up the pressure gradient. Now, our last piece of equipment is where the important refrigeration happens. Okay, and this is going to be heat transfer into the refrigerator, so out of our food or out of our house that we're trying to keep cool. So this is the important part of what we're doing here, but it's really just heat transfer. There's no work. It's just flow through pipes of various geometric configurations. And so it's just the change in enthalpy across there at constant pressure will be my heat transfer into the system. Now, I'm going to work this example in class, but you might want to go ahead and look at it and try it now. You know all the information necessary to do this, but we're going to be looking at a basic simple refrigerator. It's going to use R134A as the working fluid. Now, I've got this set up so that I chose an evaporator and condenser pressure of 400 and 1400 kilopascals. The refrigerant is going to exit your evaporator with 3 degrees C of superheat, which means it's going to be the saturation temperature plus 3 degrees. So it's going to be superheated. I'm just not telling you what the actual temperature is. Okay? This is actually not that unusual industrially, a way that people might specify things. It's going to exit the condenser after being cooled to a saturated liquid because it's an easy way to build a condenser. And our goal in this problem will be to determine the coefficient of performance. So we'll actually be doing this example in class. I want to go on and talk about one other topic before we wrap up. And this is to look at what happens if I have a real refrigerator. So, okay, the biggest concern is usually the compressor. I know I've had compressors break on me on air conditioning systems many times over the years. They also, in addition to being something that's going to be a maintenance issue, they also are going to be very strongly affected by reversibilities, or irreversibilities, excuse me, misspoke. So, for a compressor, it's like a pump, and the ideal work is less than what I'm really going to find. So the efficiency is going to be the ideal work of the compressor divided by the actual work of the compressor. H1 minus H2 ideally is going to be based on an exit state where the entropy is constant. The actual is going to be, well, whatever the actual exit is. Now, these are also going to be irreversible because heat transfer is never really reversible. The refrigerant temperature, you're not going to really get it as cold as T sub C. Okay? What you're saying, you are wanting it to be, but it isn't going to be. Okay? So, this is going to be one issue. Okay? That the temperature in the evaporator is less than what you're designing, hoping for. And in the condenser, it's going to be greater. Okay? And so this will negatively impact the importance also, or the performance also. And so we will be doing a modification of this by looking at the coefficient of performance with an 85% efficient compressor. And then we'll discuss exergy again and talk about the effect on exergy of all of these irreversibilities. And that's what we'll be doing in class